This shows a spectra of an atmospheric spectra of Venus, Earth, and Mars. And you see Venus at the top, which has a thick CO2 band, and you see Mars at the bottom, which also has a thick CO2 band. In the middle, you see Earth, and Earth looks different. Yeah, you see the water bands, the rotational vibrational bands on the left, and in the middle, you see in the red circle the ozone band. And this ozone band is present due to life, because life makes oxygen in the atmosphere via photosynthesis, and oxygen forms ozone, mostly the ozone layer. So if we were to measure this band, we could have a discussion about whether we are seeing a biosignature. Here you see the atmospheric compositions of the different planets. So you see that Venus and Mars have CO2 dominated atmospheres. Titan has nitrogen and methane. But on Earth you have 21% of O2, which comes from life mostly. And as I showed earlier, this is like the evolution of Earth, which you see in the middle here. So life has affected the evolution of Earth. It has led to the rise of oxygen and photosynthesis, and has led to the ozone layer that we see on Earth. And we don't see these large oxygen amounts and ozone layers in such amounts on Mars and Venus. So this shows Earth as a pale dot. What you see here is you see a white square near the top right, and this is a picture taken by Voyager in February 1990, and it's a picture of the Earth from 6 billion kilometers away. So this gives you an idea of how challenging this work is. So you see a quote here from Carl Sagan, which is famous. So you see that on this little dot is everything, the complete Earth, every human being, everything. The band that you see is not real, it's an artifact from the data. But I like this plot. So the processes affecting atmospheric biosignatures, I mentioned them earlier. So starting at the top, you have escape processes. The magnetosphere of the Earth protects the atmosphere. Photons come into the atmosphere. Impacts affect the upper atmosphere. Moving into the middle atmosphere, you have clouds and rainout. And near the surface, you have evaporation, condensation. You have biomass being emitted. Deposition at the surface, outgassing from volcanoes, etc. So it's a complicated system. Here is a table showing some atmospheric biosignatures, potential atmospheric biosignatures typically investigated. So you see on the left oxygen, which forms ozone. It comes from cyanobacteria. Importantly, what you see on the right-hand side is the abiotic sources. So if you measure a species, a biosignature, then you have to decide, am I really seeing life, or am I seeing something from non-life? Is it really life that I'm seeing? And you have to know the abiotic sources. So oxygen can come from CO2 photolysis or from water photolysis followed by escape of hydrogen. The second row, nitrous oxide on the Earth, mainly comes from nitrifying and denitrifying bacteria. But it can also, a small amount can come abiotically from photochemistry or from energetic particles. Methane on Earth comes mostly, maybe 90%, from methanogens, from bacteria, but maybe 10% can come from geology emissions, volcanic emissions, etc. Chloromethane can come from algae and ocean vegetation and seaweed. But there are also some abiotic sources. And written in grey at the bottom are the so-called technosignatures, so from advanced civilizations like CFCs, and I won't be talking about them so much, I'll be talking about the others. So these are important concepts in biosignature science. A false positive refers to a situation where life is there, but we miss it because maybe we don't see it because it's hidden. The spectral features are hidden by thick clouds, or there are overlapping bands or whatever, and that's the false negative. At the bottom, the false positive is the case where life is not there, but we think it is there. So we are fooled by non-life processes and we say, oh look, we're seeing a biosignature here, but it's not a biosignature, it's abiotic. So we have to assess atmospheric biosignatures in terms of like what is life and what is non-life producing them. So as I said, for oxygen, it has a biotic source, photosynthesis, in green, but the black text shows abiotic sources. So step 1, CO2 can photolyze to build CO plus O, and the O can react with itself. M here means any atmospheric species which is needed, because if the O and O come together, the conservation energy means they will bounce apart again unless there is an M there. Any molecule is M, which happens to be nearby, which can absorb the excess vibrational energy and make sure that they stay together. And they can form oxygen, O2. The second step is where water photolyzes and the hydrogen escapes, and then you're left with O, and the O can form O2 again. For methane, the biotic sources are methanogenic bacteria, but the abiotic sources of geology. So we always have to know the context in order to exclude abiotic sources. So here are some important steps. So imagine it's the future. Imagine we have next generation telescopes and they have found signals which could be biosignatures. And then what do we do to assess these signals? So we have to collect and retrieve the data, of course, first of all in step 1. In step 2, we would need signals which are statistically significant. So 5 sigma signal to noise would be good. Step 3, we check that the signal is really the species that we think, and it's not some other species, or it's not overlapped by some other bands, like CO2 and ozone bands overlap at 9.6 microns, for example. And then step 4 is the critical step. We have to know the context of the planet. We have to know about the atmosphere, about the environment, about the star, about the age, in order to make an assessment and decide whether the signal could be due to life or whether it's due to something else, some other non-life process. So for step 4, we have to really rule out all other possibilities. And if we can't do that, then the only explanation left is that maybe it's life. This is an example calculated in our group at EPA DLR. It shows the example. You see model calculated theoretical transmission spectra of a planet like the Earth with Earth's properties and Earth's biomass emissions, and we place this planet in the habitable zone around an M-dwarf star. We do this because these stars, for various reasons, have favored signals. It's easier to measure the signals. Spectroscopic signals are larger. The different lines show the different assumed oxygen levels, so different oxygen levels during Earth's evolution. So PAL means present atmospheric level. So a PAL of 1 means 21% oxygen, and a PAL of 10 to the minus 1 means 2.1% oxygen, etc. So what you're seeing here, you're seeing as we decrease the oxygen in the atmosphere, as we go from blue to light blue to green, we're seeing like a reduction in the oxygen spectral features. So if you look at the left-hand side, you see at 0.5, 0.6 microns, ozone and oxygen, the weak signals there, they virtually disappear for the green case. And you see around 1 to 2 microns, the water methane bands. You see the CO2 band on the right-hand side, the big thick band is not affected much by O2. The main message of this paper is that it's very difficult to measure oxygen signals, especially for low oxygen atmospheres, even with next generation telescopes. So the conclusions here, atmospheric biosignatures is a fascinating topic in exoplanetary science. It's expanding in the literature in preparation for future planned missions. Biosignatures are very challenging to detect and to interpret. And there I've come to my last slide. I forgot to say, when I first showed this slide, I showed the picture of a young boy, and I wonder if anybody guessed who that was. It was Albert Einstein. Here's his picture here. Anyway, that's all from me, so thank you very much, and bye-bye.